In today's hyper-connected world, high-speed internet access is no longer a luxury, but a fundamental necessity for individuals, businesses, and entire societies. While terrestrial infrastructure like fiber optic cables and 5G networks are rapidly expanding, they often struggle to reach remote and underserved areas, leaving millions without reliable internet access. This digital divide hinders economic development, limits educational opportunities, and restricts access to essential services like telemedicine and online government services. To bridge this gap, a new frontier is emerging: satellite internet. A constellation of ambitious companies are racing to deploy massive networks of satellites in low Earth orbit, LEO, promising to deliver blazing fast internet connectivity to even the most remote corners of the globe. This Space Race 2.0 holds the potential to revolutionize communication, democratize access to information, and unlock unprecedented economic growth, particularly in developing nations. However, this ambitious vision faces significant challenges, primarily centered around the astronomical costs associated with building and maintaining these vast networks. The development, launch, and operation of large-scale satellite constellations require substantial investments in research and development, manufacturing, launch vehicles, ground infrastructure, and ongoing maintenance. Overcoming these financial hurdles will be crucial for the success of this transformative technology. The promise of satellite internet: imagine a world where high-speed internet is as readily available as electricity, a world where connectivity is no longer a luxury but an essential utility. This is the vision driving the satellite internet revolution. These LEO constellations, comprised of thousands of satellites orbiting the Earth at relatively low altitudes, typically between 500 and 2,000 kilometers, promise to deliver global connectivity, reaching even the most remote and underserved areas, connecting communities previously cut off from the digital world. This includes rural and remote areas, connecting farmers, businesses, and educational institutions in remote regions with limited access to terrestrial infrastructure. Developing nations, bridging the digital divide in developing countries by providing affordable and reliable internet access to underserved populations. Maritime and aviation, enabling high-speed internet access for ships, airplanes, and other vehicles in motion, transforming the travel experience. Reduced latency, near real-time speeds, enabling applications like online gaming, providing a seamless and lag-free gaming experience for players worldwide. Video conferencing, facilitating high-quality video calls with minimal delays, enabling remote work, education, and healthcare. Telemedicine, enabling real-time remote consultations, surgeries, and diagnostics, improving access to healthcare in remote and underserved areas. Autonomous vehicles, supporting the development and deployment of self-driving cars and other autonomous vehicles that rely on real-time data and communication. Increased bandwidth, delivering high-bandwidth connections capable of supporting demanding applications like streaming 4K and 8K video, enabling high-quality streaming experiences for movies, television shows, and live events. Cloud computing, facilitating seamless access to cloud services, including cloud storage, data processing, and artificial intelligence applications. Virtual and augmented reality, VR, AR, supporting immersive VR and AR experiences with minimal latency and high-quality visuals. These benefits have the potential to transform various sectors, including education, healthcare, transportation, entertainment, and business, driving economic growth and improving quality of life for people around the world. Historical hurdles and modern innovations: past attempts to build large-scale satellite constellations, such as Iridium and Teledesic, faltered due to a confluence of factors, primarily exorbitant costs and limited demand. These early ventures faced significant challenges. High development costs. Building and launching large numbers of satellites proved incredibly expensive, with limited economies of scale. The technology of the time required bulky and expensive satellites, driving up manufacturing and launch costs. Limited demand and high user costs. In the early days of the Internet, demand for high bandwidth, global connectivity was relatively low. High user costs, driven by expensive equipment and service fees, limited market adoption. Technological limitations. Early satellites were limited in their capacity and capabilities, offering relatively low data speeds and high latency. Ground infrastructure was expensive and limited, hindering widespread access. However, several key factors differentiate this new wave of satellite internet, offering a more promising outlook. Technological advancements. Miniaturization. Advancements in materials science and electronics have enabled the development of smaller, lighter, and more efficient satellites, significantly reducing manufacturing costs. Advanced antennas. Flat panel and phased array antennas, employing sophisticated electronics and software, enable more precise beam steering, improved signal reception, and increased data throughput. Laser communication. Intersatellite links, ISLs, utilizing lasers enable high-speed data transfer between satellites, significantly reducing latency and improving network efficiency. Artificial intelligence, AI, and machine learning. AI and ML algorithms are being used to optimize network performance, predict and mitigate interference, and improve overall system efficiency. Evolving business models. Diversified revenue streams. Companies are exploring new revenue models beyond traditional subscription fees, such as B2B services, providing connectivity solutions to businesses, including airlines, maritime, and remote industries. Content delivery. Partnering with content providers to deliver streaming services directly to users. IoT applications. Supporting the growth of the Internet of Things, IoT, by providing connectivity for a wide range of devices. Government contracts. Securing government contracts for applications such as disaster relief, border security, and military communications. Strategic partnerships. Collaborations with telecommunications companies, airlines, maritime industries, and other key players are expanding market reach and creating new revenue opportunities. Increased investment. Venture capital. Significant investments from venture capital firms and private investors are fueling the growth of the space industry, providing the necessary capital for research, development, and deployment. Government support. Governments are increasingly recognizing the strategic importance of satellite internet and are providing funding and regulatory support to encourage innovation and promote competition. These factors, combined with the growing global demand for high-speed internet, provide a more favorable environment for the development and deployment of large-scale satellite constellations. However, significant challenges remain, particularly in terms of cost reduction and ensuring long-term sustainability. The cost conundrum. Despite these advancements, the primary obstacle remains cost. Building and maintaining a large-scale satellite constellation is an incredibly expensive undertaking, requiring substantial capital investment and ongoing operational expenditures. Launch costs. Launching satellites into orbit remains a significant expense, despite recent advancements in reusable launch vehicles. While companies like SpaceX have made significant strides in reducing launch costs, further innovation is needed to make launches more affordable and accessible for large-scale satellite constellations. Factors such as launch vehicle availability, payload capacity, and launch site congestion can also impact launch costs and timelines. Manufacturing costs. Producing thousands of satellites at scale while maintaining high quality and reliability presents a significant manufacturing challenge. Mass production techniques and automation are crucial to drive down manufacturing costs. Ensuring the long-term durability and reliability of satellites in the harsh space environment requires rigorous testing and quality control measures. Ground infrastructure. Establishing and maintaining a global network of ground stations requires substantial investment in infrastructure and personnel. This includes constructing and operating ground stations with high-performance antennas, high-bandwidth connections, and sophisticated tracking and telemetry systems. Ensuring the reliability and security of the ground infrastructure is crucial for the overall performance and resilience of the satellite network. User terminal costs. The cost of user terminals, particularly those equipped with advanced antennas such as electronically steerable arrays, ESAs, remains a significant barrier to entry for many consumers. High user terminal costs can limit market adoption and hinder the profitability of satellite internet services. Continued innovation in antenna design and manufacturing technologies is crucial to reduce user terminal costs and make satellite internet more affordable for the mass market. Ongoing operational costs. Ongoing operational costs, including satellite maintenance, orbit adjustments, network management, customer support, and cybersecurity measures, can be substantial. Ensuring the long-term sustainability of satellite constellations requires careful planning and efficient operations to minimize ongoing expenses. Addressing these cost challenges will be crucial for the long-term viability and success of the satellite internet industry. The road ahead overcoming these cost challenges will be crucial for the long-term viability and success of the satellite internet industry. This will require a multi-pronged approach, continuous innovation, technological advancements, ongoing research and development in satellite technology, propulsion systems, and manufacturing processes are essential to drive down costs and improve performance. This includes developing lighter and more durable materials, exploring novel propulsion technologies, and advancing miniaturization techniques. Software-defined satellites. Embracing software-defined satellites, where much of the satellite's functionality is controlled by software, can enhance flexibility, reduce development costs, and enable faster upgrades. Collaboration. Industry partnerships. Close collaboration between satellite operators, manufacturers, component suppliers, launch providers, and telecommunication companies is crucial to drive down costs across the value chain. This can involve joint ventures, strategic alliances, and open-source initiatives to share knowledge, resources, and best practices. Government-industry collaboration. Collaboration with governments can facilitate regulatory approvals, access to funding, and support for research and development initiatives. Scalability. Mass production. Achieving economies of scale in manufacturing, launch, and operations is critical to reduce costs and improve profitability. This involves developing efficient and automated manufacturing processes, optimizing launch schedules, and streamlining operational procedures. Constellation management. Developing sophisticated software and AI/ML algorithms for constellation management and network optimization can improve efficiency, reduce operational costs, and enhance overall system performance. Sustainability. Space debris mitigation. Developing and implementing strategies for space debris mitigation is crucial to ensure the long-term sustainability of the space environment and prevent future collisions. Environmental impact. Minimizing the environmental impact of space activities, such as reducing launch emissions and minimizing space debris, is increasingly important. By pursuing these strategies, the satellite internet industry can overcome the challenges of cost, ensure long-term sustainability, and unlock the full potential of this transformative technology to connect the world and drive human progress. Conclusion. The race to space is on, and a new era of satellite internet is dawning, promising to transform how we connect and communicate. While significant challenges remain, particularly in terms of cost reduction and ensuring long-term sustainability, the potential rewards are immense. By overcoming these hurdles and embracing innovation, satellite internet has the potential to bridge the digital divide, connect underserved communities, including those in rural, remote, and developing regions, providing access to education, healthcare, and economic opportunities. Empower individuals and communities. Enhance social and economic development by empowering individuals and communities with access to information, education, and global markets. Drive economic growth. Stimulate economic growth by enabling new businesses, fostering innovation, and improving productivity across various sectors. Advance scientific research. Support scientific research and exploration by providing high-bandwidth connectivity for remote sensing, environmental monitoring, and other scientific endeavors. Improve global security. Enhance national security by providing reliable and resilient communication networks for critical infrastructure, disaster relief, and emergency response. The successful deployment and operation of large-scale satellite constellations will require continued innovation, collaboration, and a commitment to sustainability. By addressing the challenges and capitalizing on the opportunities, satellite internet has the potential to revolutionize communication, connect the world, and usher in a new era of global connectivity and human progress.